In this lesson, I'm going to be finding absolute extrema on an interval. There's a four-step process by which to do this. It's outlined in the book on page 163, and that I've outlined for you in the blue box over to the right. The procedure is as follows. Step 1, find the critical numbers of f in the open interval AB. Evaluate f at each critical number in AB. Evaluate f at each endpoint of closed interval AB. The least of these values will be the minimum, and the greatest of these values will be the maximum. I just saw a typo, so let's just do this to fix it. The grade test. So since the first thing we need to do is find critical numbers, we're going to need to take the derivative. So I'm going to start by just rewriting this as f of x is equal to 2/3 x plus 5/3. Now the derivative here is going to be very simple. The derivative of this linear function is just 2/3. So now to seek out the critical numbers, the first question is, where is the first derivative equal to 0? And the second question is, where is the derivative undefined? Okay, so if we take our derivative 2/3 and set it equal to 0, that doesn't really tell us anything. So the conclusion here is that there are no critical numbers for this step of the process. Now in terms of where it's undefined, we usually look at the denominator and ask where is the denominator 0. But there isn't even any variable here, so there are no critical numbers here. So this problem actually has no critical numbers whatsoever. So if we had to formally list them, there would be nothing to list. But it might be worth just noting that there are none. Okay, now the next step of the process is, well, we did step 1, find the critical numbers. Evaluate f at each critical number. Well, there are no critical numbers, so there's nothing to plug into the function, so we can't do that, or we could say that it's done. And now we're going to find f at each endpoint. And you might want to have a calculator handy for this. So what I'm going to do is make a little chart, and I'm going to say left endpoint, and we'll say right endpoint. And we'll try to summarize this in a little grid here. We'll do x, and we'll do f of x. Now, usually on this chart, you'd put the critical numbers in between, but there weren't any. So we're just going to deal with the left endpoint, which was 0. That's coming from here. And the right endpoint is 5, and that's coming from there. Now, if you plug these values into the original, if you plug in 0, you end up getting 5/3. And if you plug in 5, you get 2 times 5, which is 10. 10 plus 5 is 15. 15/3 is 5. So we're focusing on the output, which is this, and the least is going to be the minimum, and the greatest is going to be the maximum. So we're going to have a minimum at 0 5/3, and we're going to have a maximum at 5 5. So just to be clear, when we're asked to find extrema, what we're really asked to find are minimums and maximums, or the highest on an interval, the highest point and the lowest point. Well, this is the lowest over here because it's got the smallest y value, and this is the highest. Now I'm going to just convince you by looking at a graph. I've mentioned before in my other videos that I'm a visual learner, and I really like to have the graph to see why the answers are what they are. And then when I become very comfortable, then I start not using the graph. But in the beginning, I think it's a great idea to look at the graph. So let's see, I'm going to go to the y equals screen, and I'm going to put in 2x plus 5 in a chunk, 2x plus 5 divided by 3. And I think I'm going to make it bold so you can see it a little bit better. Okay, and then for my window, I'm going to go from 0, which is my left endpoint, to 5 by 1s. And I'm going to go from 0 to 6 for my y's. All right, so I'm going to graph this. And not surprisingly, it's a line. And we're supposed to find the lowest point on this interval and the highest point. And our calculus told us the lowest point was 0 5/3. And this is between 1 and 2, that's 5/3. And our highest point was at 5 5. And if we go over, that's 5. So this is just an illustration of why the answers are what they are. In problem number 18, they ask us to find the absolute extrema of the function f of x equals x squared plus 2x minus 4 on the closed interval -1 to 1. So our first step will be to find the derivative. So let's see, we're going to say f prime of x is equal to 2x plus 2. And then we're going to ask two questions in order to find the critical numbers. The first question will be, where is the first derivative equal to 0? And the second question is going to be, where is the first derivative undefined? Okay, so let's go to the first question. 2x plus 2 equals 0. So x equals -1. And where is it undefined? Again, that would be looking at the denominator and asking when would the denominator be 0. And there aren't going to be any contributions to the critical number list from that. So overall, our critical numbers are only -1. So it's really our critical number. Critical number is x equals -1. So what we need to do now is we need to make a table where we're going to look at the left endpoint, we're going to look at the right endpoint, but we're also going to look at the one critical number that we found. So critical number. So I like to put this in a little bit of a chart form. This will be x. This will be f of x. Our left endpoint's -1, and that's taken from here. Our right endpoint is 1, and that's taken from here. And our critical number was also -1. That's interesting. So I guess your critical number could be at an endpoint. Very, very interesting. So obviously these two things are the same. We don't have to do it twice or anything. Now we could go to our calculator to figure this out. We could do this by hand. It's not that difficult, but since this is being captured for all times, I think I'm going to use my calculator in case I screw up. Maybe I'll do that. -1 squared plus 2 times -1 minus 4. That's coming out to be -5. Okay. And certainly this is also -5. Now if I plug in 1, that's 1 plus 2 is 3. 3 minus 4 is -1. So again, the minimum will be the lowest of these values, and the lowest y value that we see is -5. So we're going to have a minimum at -1, -5, which happens to be an endpoint, and we're going to have a maximum at 1, -1. Okay, so let's convince ourselves that this is right by looking at the graph. Okay, so I'm going to enter the original function, x squared plus 2x minus 4. I'll make it bold so you can see it a little bit better. And let's go to our window and let's go from -1 to 1. Now I'm expecting to see a parabola, but only a real narrow window of the parabola. It's from -1 to 1. So here's -1 over here, there's 1, and this is the portion of the parabola. Now this looks like it's the lowest point that I'm seeing, and that should be at -1, -5. So this is -1, and I drop down to here and I go over. That looks like it's about -5. Now on this interval, the highest point is over here, which is +1 and down just a little, and that's down at -1. So yeah, this confirms our answer. So the calculus that we're doing by hand is proving to be true by looking at the graph. In number 22, they're asking us to find the absolute extrema on the closed interval for the function f of x equals x cubed minus 12x on the closed interval 0, 4. So let's start by finding the derivative, and that's going to be f prime of x is equal to 3x squared minus 12. And we're going to ask, where's the first derivative equal to 0? And we'll also consider where's the first derivative undefined. And we'll start by doing the first derivative equal to 0. 3x squared minus 12 is equal to 0, which means that 3x squared is equal to 12, which means that x squared is equal to 4, which means that x is equal to plus or minus 2. And over here, There's no denominator in our first derivative, so there really is no location where it's undefined. So this is not going to contribute anything to our list of critical numbers. So this means these are our only critical numbers. And you'll notice I'm starting to take some shortcuts. I was doing these in like very specific colors. Now I'm just sort of going for it in the interest of time. Okay, so now we've got to make the chart. So our left endpoint, our LEP, left endpoint, is 0. Our critical numbers are -2 and 2. Interestingly enough, the -2 is not even in this interval, so we're not going to consider that. So that's an interesting little tidbit. Let me just say that again. There are two critical numbers, -2 and 2, but -2 doesn't fall in this interval, so we're not going to look at that. And then our right endpoint is 4. Okay, so let's just set this up here. Okay, if I plug in 0 into the original function, the output is 0. If I plug in 2 into the original function, the output is -16. And if I put in 4 into the original function, the output is +16. So if we're asked to find extrema, or absolute extrema on an interval, we're looking for the highest and the lowest. The lowest is called the minimum, and the minimum happens at, in this case, 2 -16. And the maximum, or the highest value, is going to be at 416. So let's take a look at the graphing calculator and just see if that is confirmed. Okay, so we've got y equals x cubed minus 12x. Make it bold. Go to the window, select 0 for my left endpoint, and then 4 for the right endpoint. And I'm just looking at the y scale. Some of the numbers I'm working with are -16 and 16, so maybe I'll go from -20 to 20. And I think I'll make the scale go by 4s. All right, so I'm ready to graph. Now, to me, the lowest point looks right here where the arrow is, and these are by 1, so this is 1, 2, and down here, 2 -16 is supposed to be the lowest. Now, these go by 4, so it's -4, -8, -12, 16. So yeah, I'm buying that the lowest point is at 2, -16, and the highest point's at 4, 16. 1, 2, 3, 4, and then this is 4, 8, 12, 16. Yep, so once again, the graph confirms the calculus that we did by hand.